Hello, and welcome everyone to our RISE online seminars. Today, Thomas Marchioro will give us a presentation on how to process private data. So, Thomas, the floor is yours.
Okay, thank you very much, Ludovico. Hello, everyone. I am Thomas Marchioro, and welcome to this webinar about how to process private data. And by the way, if you have any questions, feel free to interrupt me anytime and ask. So let's start with the motivation. Well, the motivation is kind of obvious. Basically, why do we need a specific way of handling private data? But the idea is that there are some kind of data that the users are not willing to share unless they are 100%, well, or not 100%, but with some percent sure that they won't be leaking any private information, and in particular that they cannot be like re-identified from the processing of their data, and that some like other private information cannot be inferred about them. So like, yeah, the setting is the following. We are like some analysts or some guys who want to like compute some statistics or train some machine learning model, and we want to earn the trust of these guys who need to disclose their data, and we have to guarantee that we won't do any bad use of their data, and we won't actually be able to do any bad use of their data. And so this is pretty much the motivation, and this is the outline of the topics that I will be covering during this presentation. First of all, I will try and explain why anonymization is not always the best solution, and in particular, it's not the best solution when it comes to actually process the data instead of just observing them. And after giving this like brief motivation, I will introduce the concept of differential privacy and the setting of differential privacy. And then I will move to two practical applications, which are differentially private machine learning and local differential privacy, which is what it is used in practice by big companies such as Google and Apple, because it is decentralized and it's completely, it doesn't require any trust in the company. Like all the processing is done locally by the users. And then I will discuss some open challenges that basically cover the cases when differential privacy is not enough because it introduces too much noise and makes the data unusable. And so I will be covering what can we try to do in those cases and what the research is about for those cases. So let's start by talking about why anonymization is not always the best solution. Well, let's remind us like what is anonymization, and in particular, what is k-anonymity. Remember our original problem that we discussed during the past seminar, which is basically we have a data set that we want to disclose, and we want basically to prevent users inside this data set to be re-identified. So we've seen last time that it is not sufficient to just remove their names, because there might be some attributes of them that allows re-identification. For example, in this case, let's say that we know a user that is in this data set, which is called Bob. And we know that Bob is 60 years old, and that is approximately 180 centimeters tall, and that he is a male. So if we disclose this aggregated data set with just like the names removed, we are still able to see that the only entry satisfying these attributes is actually PO2. So like we can tell we can re-identify Bob and tell that Bob is actually PO2. And when we have done that, we are able to infer some additional information about Bob. For example, in this dataset, we are able to tell that Bob has some disease that is stored in this column. So what k-anonymity does, it tries to basically remove some information by generalizing and or suppressing some of these attributes, which are called quasi-identifiers, and it does this until for each entry there are at least k-1 other entries which share the same tuple of quasi-identifiers. So, for example, you see that there are two users which are like 180 centimeters tall, and the other are either greater or older or younger than that. No, sorry, they are taller or shorter than that. So, with this way, basically, we are not able to tell to identify a specific user in this data set because basically there are always two identical entries. Nonetheless, this might not be sufficient in some cases. In particular, although this prevents like the re-identification attack that we discussed before, it doesn't prevent an inference attack. So we are still able, for example, to tell that regardless of whether Bob is PO2 or PO9, we know that only these two users are 180 centimeters tall. So like either of these two users are Bob, but both these users have the disease. So like regardless of who is Bob of these two users, we still know that Bob has the disease. And okay, so we have this problem, and so like how do we solve it? Well, we can think of anonymize further the dataset. Like instead of applying just k-anonymity, we can apply another guarantee, which is called L-diversity. And basically what L-diversity does, it ensures that there are in every k-anonymous group, there are at least L different values of the sensitive data. So, for example, this data set now is true anonymous because there is a unique k-anonymous group, and there are two different values that are either yes or no. But as you can see, of course, this is like a toy example, so like we will easily lose a lot of information, but in a most general case, applying k-anonymity plus L-diversity will result in a huge loss of information. And when we want not only observe the data, but we want to actually use them in some way, like either compute statistics or do machine learning or compute any function, doing this, most cases, makes the data completely unusable. So let's try and see what can we do instead. Well, the concept of differential privacy has been built with this exact concept in mind. Basically, the idea is that in most cases, like actually we don't care about seeing the data of the users. We don't want to see the data of a specific user. We don't want to see the data of Bob. What we want to do is we want to either compute some aggregate statistics or to compute a general function of the entire data set. Even what we do when we do machine learning, for example, we try to minimize some loss function with respect to the entire data set, not to a single user. So the setting of differential privacy is that the analyst won't be able to see the data, but will be enabled only to ask some queries. So some aggregate questions about the data. For example, tell me the number of males who have the disease. Of course, to ask these kind of questions, there must be someone who has access to all this data. And in this differential privacy setting, this person is called the curator, and is basically a trusted entity who has access to the whole data set. And this entity will compute the statistics and will send the results to the analyst. And this seems like a pretty straightforward and a pretty safe idea. But the problem is that query is a very broad concept, and in principle, there might be many things that can go wrong with this setting. In particular, we don't specify which kind of queries are safe. And the analyst, in principle, could ask very specific queries that have only like one answer, like only one user as answer. So, for example, the analyst may ask, okay, give me the count of the 30-year-old females who have the disease in the database. And there is only one user satisfying these requirements. And so the analyst will gain information about this specific user. And if the analyst asks enough of these specific queries, he will eventually be able to reconstruct the whole database, which is exactly what we want to avoid in the first place. And this is where differential privacy comes into play, because differential privacy actually gives us a guarantee that it doesn't matter if a user is present or not in the database. Like the result of our query that we execute, of the algorithm that we execute, won't be much different. Like in order to like understand differential privacy, we need to basically break down its definition a little bit. So an algorithm is epsilon differentially private if for any adjacent datasets x prime and any set of outputs, this constraint holds. So like, first of all, let's specify what are adjacent datasets. Adjacent datasets are datasets that differ in only one row, which means basically there is one user of difference. Like basically we take one user in database X and we substitute it with another user. And when this happens, this constraint must hold. Basically, this constraint is about the distribution of the output of a certain mechanism that we apply to the data set. And basically, the ratio between the distributions should be bounded by this value e to the epsilon. And epsilon is called the privacy budget, which is the smaller the better. So like a smaller epsilon means higher level of privacy. And so let's try to visualize what does this mean. Basically, let's say that these are two adjacent databases, and the output in principle might follow these two distributions. Like the output is random, and it follows like these two distributions depending on which of the adjacent databases you have chosen. So the differential privacy constraint requires that for any couple of points for a same outcome, the ratio between the probabilities is bounded by this value e to the epsilon. So basically the idea is that the probability of a certain outcome shouldn't differ so much regardless of which of these two adjacent data sets you're using to process your data. So let's give a couple of remarks about this definition. Notice, first of all, that the definition is symmetric, so it provides both an upper and a lower bound. So basically it means that we can apply it basically to x with respect to x prime, but also to x prime with respect to x. And so basically, like, it's not like asymmetric, but it binds the probability both ways. And also when epsilon is very small, like this weird value e to the epsilon actually becomes close to 1 plus epsilon and 1 minus epsilon, which seem more reasonable values, sort of like more intuitive values. But the reason why we use this e to the epsilon is it's because of this composability property of the exponentials. In particular, if you apply the definition multiple times, you can find that for a pair of data sets that differ in m rows instead of like only one row, so they're not adjacent, but they have like m entries of difference, still like a less tight bound holds, which instead of being e to the epsilon is like e to the m epsilon. So it means that even if we differ by multiple rows, still we have like a smooth privacy decay. So yeah, now we have basically described the definition a little bit and we have breaking it down a little bit. But let's see how we can actually enforce differential privacy in a mechanism. So remember, our objective is to ask some query, like as analysts, and to receive basically a response, which nonetheless it's randomized. So like because if it's not randomized, we are able to ask so many queries as we wish, and we are able eventually to reconstruct the initial database. So that's why we need randomness in our responses. So what kind of randomness can we employ to save as much information as possible? Well, basically, we use the Laplace mechanism, and I won't go into details, but basically the Laplace distribution is sort of similar to the Gaussian distribution, but it is a little bit more spiky, because it's like a two-sided exponential distribution. And yeah, well, if you try to apply this definition, since like its distribution is sort of exponential, you will see that it exactly satisfies the requirements of differential privacy, as long as we apply it with this like scale parameter. Scale parameter is basically as the same as sigma for the Gaussian distribution. Basically, it determines how broad, how wide is the range covered by the distribution. And if we apply Laplace with this parameter, basically we have that it depends on delta. Delta is the maximum difference between that can happen in the query that you are asking by changing one row in the data set. So basically, if instead of asking the query about dataset X, we ask the query about X prime, which differs in one row, we can get a difference in our response, which is at most delta. And it makes sense that the noise that we have to apply is actually depends on this value delta, because the larger could be the difference in this query, the more we have to compensate for this difference with noise. And also it is inversely proportional to epsilon, which means that we need to apply more noise when when we want like stronger privacy guarantees. And of course, these privacy guarantees sacrifice utility. So at the end of the day, it's a trade-off between the utility that we need and the privacy that we want to guarantee to the users in our dataset. So again, let's see the role played by these sensitivity values. So we have seen that, that basically this sensitivity is how much our query can change if we change one row of our dataset. So let's try to explain it more concretely. In this dataset, we have some users, and basically, let's say that the analyst asks a counting query. So accounting query could be, for example, tell me the number of users who are males and who have the disease. And in this case, the answer is 4. So this value of delta in this case is 1, because if for example we change like one of the users from for example user P10, we change it into a male with the disease, the counting query will be 5 and not 4. So basically a counting query can be changed of at most one value if we change only one row. And therefore, like the Laplace noise that we need to apply is 1 over epsilon. And you can see that, for example, if we apply epsilon equal to 1, we have like an average error which has magnitude 1, which means that, for example, the answer could be like on average 4 or 5 or 3. And so like basically the idea is that we could sort of compensate for like one extra user or one less user with the noise. So like if the answer is 5, it could be either because like there is one extra male user with the disease, or because we have added this Laplacian noise and it just added a value of 1. And so this is how differential privacy is enforced. There is also a relaxed definition of differential privacy, which is called epsilon delta differential privacy. And basically, the difference is that we don't allow only this multiplicative factor with respect to an adjacent dataset, but we also allow an extra value delta, which should be in principle very small. And what it means, if we go back to this like different distributions, this similar distribution, is that, one second, is that, for example, instead of allowing only this multiplicative difference, in some cases we can allow like an extra difference of delta. So something like this, we have like a spike here, and the maximum size that we allow for this spike is actually delta. Okay, this wasn't supposed to happen, but I hope you got the idea. Okay, so now let's see some practical applications of differential privacy, and in particular, let's see differential privacy applied to machine learning. So because at the end of the day, of course, most of the times we won't be asking counting queries or average queries, but we want actually to like, I don't know, train some models on our data or do some complicated statistics. So with machine learning, probably the most popular models nowadays are neural networks. So we have to ensure that they work fine on our differential privacy setting. And a paper published by some Google guys in 2016 in collaboration with Ian Goodfellow from OpenAI basically introduced an algorithm for differentially private stochastic gradient descent. And the idea is that the algorithm is actually very similar to stochastic gradient descent, but there are like 3 main differences. So like the first main difference is that like actually the samples won't be taken with fixed size batches, but they will be sampled at random, like with this technique, which is called Poisson sampling. And basically the idea is that the size of the batch will be varying. So like basically each entry in the database will be selected with the probability L over N. So on average, we will get a batch of L samples, but we could get either many more or many less. And after that, we compute the gradient, nothing new. Like this is present also in normal stochastic gradient descent. But what we do afterwards is we clip the gradient. And the reason why we need to do that is because we need basically to bind the value of the sensitivity, because this is what allows us actually to enforce differential privacy. And after that, we need to do what actually enforces differential privacy, which is applying Gaussian noise. We apply like the Gaussian mechanism, which is which basically, instead of enforcing like epsilon differential privacy, enforces epsilon delta differential privacy. And notice that this noise will be proportional to the maximum value that we allow for our gradient. So like that is another parameter that we will need to tune. And yeah, that's about it for differential private SGD. If you want to see more, you can go and read the paper. Basically, the results, like in the paper, they're not very comparable to, like, of course, not private, non-private machine learning. But still, they achieve some accuracy, which is definitely much better than random choice, basically. So I think this is like a good starting point. And actually, this is not only like a theoretical work, but there is a Python library which is called the TensorFlow Privacy that allows you to train your model under a differential privacy setting. So like exactly using this differentially private stochastic gradient descent. And you can go, it's open source on GitHub repository, and you can check it out. Other than that, there is not only stochastic gradient descents and neural networks. There are other differential private algorithms. I won't be covering that, but there is a recent paper which was published at Secret, which basically compares the performance of different classifiers under differential privacy. In particular, we have like naive Bayes, support vector machines, and decision trees. And of course, you can see that the main result is that, as expected, when you have a very high level of privacy, the accuracy that you can get is very low, because basically you introduce too much noise in your data, and you make them completely unusable. But on the other hand, when you relax this privacy constraint, so like you allow a higher privacy budget, you get that the results are sort of comparable with the original classifiers, which is good. Basically, the idea is that these differential private machine learning algorithms allow you to establish a trade-off between utility and privacy. And now let's go to the other main topic about differential privacy, which is local differential privacy, which is what it is used in practice by many companies, like many big companies like Google, Apple, and for sure there are others that I don't remember at the moment. So this is like our differential privacy setting that we described before. Basically, there are these users that send their data to a trusted curator, and then this trusted curator is in charge of sending this basically this noisy query to the analyst, so he can do whatever he needs to do with the result of this query. But this is actually a very it doesn't really remove the problem, because it just moves the trust barrier from the analyst to the curator. But again, we need basically a trusted guy that to which we send the data. And this is not very feasible in practice most of the times, because why should we trust this guy instead of this guy? So what we want to do in our local differential privacy setting, we want to remove the curator, and we want to directly send something to the analyst. But of course, this something cannot be your original data, because otherwise you have killed the whole point of differential privacy. But what you need to do is you need to send a noisy version of the data, and the noise must be applied in a way that still allows the analyst to compute some query. And you may wonder now, because before we have been talking about anonymization, and we said that basically anonymization is disclosing data, but removing the sensitive information. So how does this differ from anonymization? So basically the idea is that in k-anonymity, you sort of you allow you don't allow any false information. Basically, you provide 100% true information, but you just generalize or suppress it when it discloses too much data about you. Instead, in this local differential privacy setting, you actually allow to the user to send false information, but you do it in a way that if there are enough users applying their privacy preserving mechanism in the same way, you will end up collecting data which follow the same distribution. So you will still be able to perform your query or whatnot. And a trivial example of local differential privacy is called a randomizer response. What the randomizer response does is super simple, and it allows you basically to compute the average of yes/no questions. So basically of binary questions. An example could be that we are some analysts and we want to estimate how many out of n participants have exercised today. So basically, in order to do that, we assume that they don't want to disclose this information publicly and not anonymized. So we tell them to disclose instead of disclosing their actual information, so their actual bit of information, they disclose this thing. Basically, they disclose the actual information with a certain probability, and with some other probability, with a complementary probability, they disclose the complementary information. And so this way, in principle, you cannot tell which is if the answer that they have provided is actually the truth, because they could claim, no, I got into this case, into this second case, and so I disclosed actually the opposite of my information, or actually I disclosed the truth. You cannot know, basically. And what they do is they compute this value and they send it to the analyst, and the analyst just computes this value, which is an unbiased estimator of the average of these answers. And so this way he can estimate how many of these participants have exercised today. And this is completely differentially private. Actually, if you do the math, employing these probabilities, well, basically the idea, you can see that these probabilities appear very weird, but the catch is that the ratio is actually e to the epsilon. And so like if you do the math, you will find out that using this mechanism will enforce epsilon differential privacy. And if you have enough users, you will be able to compute your good estimation of the number of participants who have exercised. Okay, so yeah, this is basically like a quick sketch of why like epsilon differential privacy is enforced. But like aside from that, like the problem is how do we pay for this local differential privacy? Like, is it for free? And of course, the answer is no. What we get is like much more error. And so like the problem with that is that excuse me 1 second. Okay, sorry. Yeah, I was saying the problem with that is that we introduce more error in our response, in our query that we ask. And so the idea is that we need even more data to ensure that like our result is somehow accurate. And nonetheless, this is what it is used in practice by big companies because they don't have a problem of lack of data, but they have a problem of like building trust in their users. And so like, for example, there are these two mechanisms which are like publicly available. From Google, there is this report, which is used to collect reports from Chrome users. And the source code is actually publicly available on GitHub. And then there is this like a mechanism from Apple that is used to collect word emoji usage from their users, basically. Okay, so that's about it for differential privacy. A main problem that I hope you got from the previous discussion is that actually differential privacy requires to introduce a lot of noise, and this often like makes the queries, the results of these queries, completely unusable or partially unusable. So what can we do when we cannot afford to apply differential privacy? Well, basically, what can we do is we can go for more tailor-made solutions, basically, because differential privacy has this strength, which is a sort of like one-size-fits-all solution. Basically, doesn't matter what kind of query you're asking, there is a way of enforcing differential privacy. But the way you pay this is that since this solution is very general, you have to introduce a lot of error. So like the other way of tackling the problem is to go like more in depth of what is the query that you're trying to ask and what kind of data are you're trying to use, and to try and build some more specific solution. In particular, a solution which is been gaining popularity in later years is called like release mechanisms. And this release mechanism basically often rely on adversarial neural networks in order to basically provide a privacy preserving release of your data. And they use some like complicated loss function with some utility feedback. So like there is some information that you want to try to preserve, that in this case might be your query, and the privacy feedback, which is basically how much your information you are able to gain about the user by disclosing this data. And this is basically what I'm currently working on right now in the context of basically daily activity data. Okay, this pretty much concludes the presentation, and I have some like take-home messages in case you have fallen asleep during the presentation. So first of all, like remember that anonymization is not the best solution, especially when we are aiming at computing some statistics or to train some machine learning models, or in general to do some computation on the data. And instead, like differential privacy is actually made specifically for this purpose. But the problem that it has is that it needs a lot of data to provide accurate results. And if we want to move it to a decentralized setting, which is local differential privacy, we actually need even more data. So we pay even more, like the privacy that we get. So when we don't actually have a lot of data that are required to enforce differential privacy with a reasonable utility, we need to go for more ad hoc solutions, which try to introduce noise in a more smarter way, basically, and that take more into account the distribution of your data and the query that you're asking. So yeah, this pretty much concludes the presentation. I want to thank you for attending, and I'm open to take any questions.
Thank you very much, Thomas. So are there any questions?
Yeah, I have a couple. Thank you, Thomas, for your presentation. And I have a couple of questions that I need to, it's more about understanding, make sure that I understand what you presented today well. So if you allow me, I will go in order of your slides, okay?
Sure. Please go ahead.
Thank you. First, when you talked about the anonymization, you said it doesn't work with any kind of computation on the data.
Yeah. Sorry, go ahead.
Yeah, and you give an example where we had to kind of hide. Yeah, this slide, suppress all the data, and therefore you hide the data, but apparently can use it, right? Is this a realistic scenario? I mean, does that really happen? Because now I see no pictures on the second table.
Yeah. I think I see your point. Basically, you're asking if in practice, because this is a toy example, of course, I couldn't show a table with like 1 million of entries, for space constraints, but you want to know if in practice it happens that all the information gets canceled from the table, right?
Yeah.
I mean, yeah, in general, you won't get all the information suppressed because, yeah, that would kill the whole point. But you will get, normally anonymization actually requires to sacrifice a lot of information. There is a lot of research about optimal key anonymity, clustered key anonymity. Basically a lot of smart ways to try to preserve as much information as possible. But at the end of the day, the problem is that this kind of anonymization, the deal is that this anonymization is not done with like in mind, like some computation to be done. Like so anonymity doesn't have the purpose of making you do this some computation on this data. It's meant only to make you like observe them, and if there is some information which has been preserved, you know that this information is true. So like if I go to user, I don't know, P01, and the information that has been preserved is that this guy is a male, we know that for sure he is a male. But this is not useful when you're actually trying to make some computation on the data. When you're trying to make some statistical computation, what is your interest, what is important for you, is that the distribution, the overall distribution of the data is kind of preserved. So like that the result of your query, like or whatever you're asking, in the end will be correct, even if like a single entry like is modified somehow. So yeah, I hope this answers your question.
Yeah, yeah, it actually does. So I think anonymization can be a good solution if you are if you have like a query and you're looking for more of a statistical answer. In that sense, I can preserve the mean distribution of the data, so you still get your answer. But if you observe the data right away, you will not be able to see to profile people, let's say.
Yeah, exactly. Basically, like, yeah, the idea of anonymization usually is that you want to disclose some other kind of information, and you want to still like maintain some some kind of some information about these users, but not enough to allow to identify them. So, for example, just to say, okay, we have like some users who are like above 180 centimeters. This doesn't give any identification value, but for example, it lets you know that these users are tall, something like that. So yeah, the idea is that you want still to preserve some information, but not enough to identify them.
Yeah, yeah, I see, I see. It's more of a general information, general, yeah.
Yeah.
Okay. So also, second question about I really didn't get the differential privacy. I really didn't get the two when you have two distribution. Yes, this one.
Yeah.
Uh,
Sorry, one second. Let me erase the board because I had some problems with my mouse, I think, but okay, whatever.
yeah,
Yes,
I really
sure.
didn't get here what I mean, what this represent. The
Oh,
distribution
okay.
of
Yeah,
the.
let me explain it more, yeah, like more in details. Basically, the idea, so like, let's go back to the constraint. The constraint is this one. Basically, you have the distribution of of the result of your query given a certain data set, and the result of your query given another data set that differs by one row, only one row, nothing else. Like all the rest is preserved, but one row is different.
Mm-hmm.
So the idea here is that so like the distribution of the output will change because you have changed the data. So the distribution of the output will change as well. But the point is you don't want this distribution to be too much different. And instead of like enforcing like an additive constraint, so like you don't say, oh, I want this to be like only 0.1 more than this, you set a multiplicative constraint. So let's say that let's say for simplicity that epsilon equal to logarithm of 3. So like if epsilon equal to logarithm of 3, it means that this ratio should be lower than 3, which means that in each point, the probability density of a certain value, so let's say that this outcome here is 10, okay? Well, I am not really able to write with this mouse, whatever, but let's say that this point here is 10, okay? And we want that the probability of getting 10 according to this distribution, so like this like dashed distribution, should, and so the ratio between like this distribution and this distribution, this other distribution, which is like of an adjacent data set, so like of an adjacent of a data set that differs by one row, the ratio should be bounded by this value. So the idea is that it's a constraint that says, okay, these two values shouldn't differ too much.
Mm-hmm.
I hope it is clear now. If not, let me know.
No, I understand actually. Thank you. But also, you later, I mean, you said for differential equation, it requires a lot of data to work well.
For differential privacy,
Sorry,
yeah,
yeah.
Yeah, you require a lot of data. You're correct.
But how? How actually? Because you want to have like a representative distribution.
Yeah, the idea. Okay, let me go back to this example. And why do you need a lot of data? So here you see that if you substitute one row, you need to add this kind of noise, Laplace of 1 over epsilon.
Mm-hmm.
And let's say for simplicity that epsilon equal to 1. So like basically it means that on average you will get an error of magnitude 1. So you could get as answer 5 easily, or you could get as answer 3 easily. So you see that if your answer is small, you will get a lot of like this noise will impact you a lot, because there will be a lot of difference between like 3 and 5. But instead, like if you're asking how many males have the disease, and your database actually is a data set of billion of people, in that case, like having one like a difference, an error of 1, it won't be much for you. Like you don't care if you have like I don't know, 500 or 499 or 501. You understand? Like basically, the idea is that the more data you have, the more the less the noise will impact your results.
Okay, but I can see this the other way, the other way around. So if you have actually big data, enough amount of data, then the Laplacian values that you add to change the distribution a little bit, it will be negligible at some point, and it will be equal to like not the two distribution will be very close anyway, and it will be like you have done nothing.
Right. Yeah, but that's exactly the point, because differential privacy is meant to do exactly that. Basically, if you have a query which is private per se, it won't modify it so much. Like the point is that instead, differential privacy wants to allow you to compute any query. But if the query is too specific, so if it includes only like a couple of users in the result of the query, you want the result to be completely destroyed. So that's the point. Like, but you're right. If like you have like million of users, these distributions be almost identical, and that's the whole point actually.
Yes, yes. So I think if you have to choose the Epsilon value to be in line with the amount of data that you have, the amount of the data that you get as an answer to a specific query.
Sorry again.
So I mean that you need to choose your Epsilon value to be given the amount of the data points that you will get as an answer, or the values that you will get an answer to a specific query. So if the value is big,
right. Basically, like it's this thing. Basically, this Laplace noise that you add is proportional to the maximum variation that you can have in the query. So like if you have a counting query, your variation can be at most 1. So like you need to add noise which is like proportional to this 1 value. Okay. If you have like a query that can change of I don't know, of 500, if you substitute 1 user in the data set, then you will need to add much more noise. That's the point.
Okay. So I have lost 2 questions. I'm sorry if I am bothering you.
No, not at all. Thank you.
The slide about randomized local.
This one, local differential privacy randomized response.
Yes. So this one, I think this one example, this was an example of differential, so it's still differential privacy, right?
Yeah, it's local differential privacy, basically the decentralized version.
Okay, but how it's, okay, I see that the probability you put here for x of I and 1 minus x of I, it's the same probability, but it's a complementary probability.
Right.
Okay, so I didn't really get how it works, because how it's local.
Oh, it's local simply because here you don't like normally what you have is that this curator like takes all this data, computes the query, and then adds the noise. Okay, this is how it's done, like in basically decentralized differential privacy. Instead, what you have in this local differential privacy is that this user computes locally this random variable z, so it doesn't need to send it to any curator. like it just like computes it locally and then sends it directly to the analyst. And the analyst cannot tell much from this ZY because like it could be like, you know, it could be either that he actually disclosed the true information, but it could be that he like, you know, he tossed a coin with the probability 1 over this value, and he got actually the opposite of his answer. So that's the idea. Basically, he sends the answer, but with some probability it's flipped.
Okay, but so he can say the actual answer like x of I, or sometimes he says the complementary value.
Right.
Okay, but wouldn't be still that should still give you I wouldn't say like wrong answer if you do the complementary value. If you give the complementary
sorry
value.
again.
It would be not like giving a false answer if you give
exactly. But the idea is that okay, the idea is that with the higher probability it will disclose the true value. With lower probability it will disclose the other value. Let's say that these probabilities are actually 3/4 and 1/4. But like at the end of the day, the adversary, like he could still claim, okay, I got the probability 1/4, so like I actually disclosed a false answer, or I didn't and I disclosed a true answer. You cannot know. So that's the point. This introduces uncertainty, but the point is that if you have a lot of users who do that, on the large numbers, you will get the true distribution, that these values follow the true distribution, because like an equal number of values will be flipped.
Yeah. Okay. The last question I have is I've been working lately on how to maintain a privacy data, the user privacy in decentralized fashion when using blockchain. Okay, and we, from what I see so far in the literature, it seems that every time someone applies some technique to encrypt the data, and still you can train your machine learning model on this encrypted data, but there is a big drop in the accuracy. So as someone who working with privacy, do you see any way that I can still maintain a decent result machine, like a classification model, while maintaining the privacy of the user, to have some good degree, like a sweet spot between both of them?
Yeah, that's actually a very good question. I'm not. I mean, I will try my best to give you an answer, but I'm not sure if anyone is fully entitled to give an answer to this question, because it's sort of open question. But basically the idea is that, first of all, you have to choose the right trade-off between privacy and utility. So like that's the whole point. Like, and after you have done that, like, so after you have said, okay, I've guaranteed like as much privacy budget as I can, what you have to do is you have to collect as many data as possible, because the more data you have, the more applying, for example, a privacy preserving mechanism won't bother too much your machine learning algorithm. And finally, when you see that a differentially private mechanism doesn't work, you have to try and like go deeper in your specific application, because the point is that like most people try to go for the super smart general solution that applies to everything, but the point is that there is no such thing as one size fits all. Like when you have a specific problem with specific data, in order to get like a decent solution, you have to look at your data and see how you can enforce privacy while still preserving utility. Because like there might be a lot of things that differential privacy overlooks, because it goes for some like very general rules in order to apply the noise. And so like maybe you could see how instead you can avoid using, basically use some like relaxed definition in your setting, or just find a way of enforcing like the same privacy constraint, but in a smarter way and while saving your utility. I know it's a very general answer, but you know, truth is that there is no like yeah, like there is no universal solution. That's the problem.
Yeah, but actually it's a good answer. Thank you, Thomas.
Thank you for the questions.
So do we have any other questions, guys? If not, I would like to thank again Thomas for the very interesting presentation and discussion, and see you all again in 3 weeks for the next seminar. Thank you and bye-bye.
Thanks a lot. Bye.